Hello everyone and welcome back to Educator.com. I'm Dan Fullerton, and in this lesson we're going to talk about conservation of energy, one of the most useful concepts in the entire course. Our objectives include stating and applying the relation between work and mechanical energy, analyzing situations in which an object's mechanical energy is changed by external forces, applying conservation of energy in analyzing the motion of objects, and solving problems that call for applications of both conservation of energy and Newton's laws of motion. So let's start by talking about conservation of mechanical energy. Let's consider a single conservative force doing work on a closed system. In that case, we know that the work done by that force is the change in its kinetic energy by the work energy theorem. But we also know that the work done by that conservative force is the opposite of the change in its potential energy. So if those two are equal, we could then set the change in kinetic energy must be equal to the opposite of the change, that's the change in potential energy. Or rearranging this slightly, change in kinetic energy plus change in potential energy must equal 0 for some closed system. And if we expand this out a little bit, what we're really saying is the initial energy must be equal to the final energy, or kinetic initial plus potential initial must equal kinetic final plus the final potential energy, the conservation of mechanical energy. But what if you have non-conservative forces? Well, non-conservative forces change the total mechanical energy of a system, but not the total energy of the system. The work done by the non-conservative force is typically converted to some sort of internal or thermal energy. So if our total energy is kinetic plus potential plus the work done by non-conservative forces, and the total mechanical energy we're going to define as just the kinetic plus the potential. Let's look at some examples here. We have an object of mass m that falls from some height h. Find its speed immediately prior to impact using conservation of mechanical energy and neglect air resistance. And of course you could do this with the kinematics you already know, and I'd recommend after we do this problem here with energy, take a minute and try it with kinematics. Make sure you get the same answer. All right, we have our object. There it be. It's going to fall some distance to a new position. Right there it has some kinetic plus potential energy, initial. Down here it has some final amounts of kinetic energy plus potential energy. And it changes its height by an amount, h. So, writing our formula for conservation of mechanical energy, because we're only dealing with conservative forces here, we're neglecting air resistance, the initial kinetic plus the initial potential energy must equal the final kinetic plus the final potential energy. Well, it starts at rest, so the initial kinetic is 0, and the initial potential energy is mgh, assuming we're in a uniform gravitational field. Its final kinetic energy is 1/2 m times its final velocity squared, and its final potential energy is 0 because it's at its final point, what we're calling 0. So we can simplify this. We can divide an m out of both sides to say that gh equals v squared over 2, or velocity squared equals 2gh, and if we want just the speed, that's going to be the square root of 2gh. All right,